This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class, and we're at lecture 46. On the topic of lithography, we'll be talking about defocus, the effects of defocus on an image, and depth of focus, which we usually abbreviate DOF, and we sometimes say DOF, and sometimes we pronounce it DOF, although I'm not that kind of a person. I say DOF. Defocus. Specifically, defocus is an error in the positioning of the wafer relative to the plane of best focus. So the first thing we have to understand is, what does best focus mean? In a very simple optical sense, best focus occurs when the optical path length of all the rays emanating from the mask and landing on the wafer or near the wafer are all equal. So the optical path length of the 0 order and the +1 order and the -1 order are all equal. At the place they're all equal, that's where best focus occurs. Now, optical path length, what is that? You see that the path lengths certainly aren't different. The 0th order has a much shorter path length than the first orders. But the optical path lengths are the same, and that's because of this lens. The lens is made out of a material like glass with a refractive index that is bigger than 1. Refractive index of air is 1. Refractive index of glass is on the order of 1.5. Some optical materials 1.6 or even higher, but on that order. When light travels through an optically dense material like glass, it slows down and its wavelength is compressed. So this same distance of light traveling through glass compared to air goes through many more cycles. In fact, a factor of the refractive index, more cycles through that same thickness in glass versus in air. So the optical path length is the physical path length multiplied by the refractive index of the material. Now, the plus and minus first orders are obviously traveling longer physical distances. But because they travel through the thinner part of the lens, and the 0th order travels through the thicker part of the lens, in fact, the optical path lengths of all of these rays are the same. And when they arrive at a place in phase with each other, we say that is where best focus will be. It will be here. Now, what about here? I move some distance away. Are they still in phase? Well, now the 0th order and the plus and minus first orders have traveled different distances to get to the wafer. The first orders have to travel a farther distance to get to the wafer compared to the 0 order. That extra distance translates into extra phase, and as a result there'll be a phase error or a phase difference of the first orders compared to the 0 order whenever the wafer is not at the plane of best focus. We're going to explore how much the phase is off and how it affects the aerial image in the next few slides. One way of thinking about defocus is to actually geometrically calculate what the path difference is. So consider the exit pupil of the lens, right? So this is the bottom of the lens where the light is coming out. And if I have light focusing down to a point on the wafer, here I show the wafer coated with a little bit of photoresist, that means there's a certain curvature of the wave of light that has the right radius of curvature, so that all the light from all of these different points on the wavefront will converge down to that wafer point in phase. So all of the points on the wavefront are in phase, and they all travel the same distance to get from this spherical wavefront down to the wafer, so they remain in phase when they combine at the wafer. Now, let me take this wafer and simply move it a distance delta away. So if I wanted the wafer to be in focus, I'd have to move it a distance delta up. The light is all focusing down to this point, but my wafer is off. It's, again, out of focus by a distance delta. What does that mean? Well, if I use kind of the attitude of the customer is always right, the wafer is always right, I can say that the actual wavefront is what's wrong. Why? Because it's focusing up here, but I put my wafer over here, so what I really want is the light to focus where my wafer is. Well, it's not focusing there. It's focusing over here. Excuse me. It's focusing over here instead. So I can imagine what a wavefront would look like if it were to focus where my wafer actually is. So here in the red, I have created a new wavefront, my imaginary wavefront of what I would actually like to have happen. So here in the black, that's what actually happens. The red is what I want to happen. And there's a difference. The difference is the optical path length, optical path difference. So from here on, these two rays travel about the same distance, but in order to focus on the wafer, there's an extra distance that the light would have had to have traveled. I'll call that the optical path difference. Now, the defocus that I'm showing in this graph is highly exaggerated. We have defocus distances on the order of tens of nanometers or maybe microns, and these radius of curvatures, this L sub I, the image distance from the lens is on the order of centimeters. So this picture is a gross exaggeration just so you can see these differences. But we can use a little bit of geometry. It doesn't take a whole lot of geometry to calculate what that OPD is as a function of the angle theta. You see that here in the center there's no difference in the phase, and that the phase difference grows the further away I get from the optical axis. That is, as theta gets larger, this optical path difference grows. And in fact, we work out the geometry, we find that the optical path difference is the defocus distance delta multiplied by 1 minus cosine theta. So when theta is 0, I have no optical path difference, and as theta gets larger and larger, then the optical path difference grows. Well, we can make a small approximation. If we have small angles, we can approximate 1 minus cosine theta as being about equal to sine squared theta over 2. If you want to figure that out, just use the square root relationship between cosine theta and sine squared theta, and then do a Taylor series expansion of the square root. But in any case, I can make this approximation. If the angle theta is relatively small, OPD is about equal to delta sine squared theta over 2. Why would I care? Why would I want to make that? I mean, I can calculate cosine theta just as easy as I can calculate sine theta. Well, here is why. We often do our calculations in terms of the spatial frequency. Remember the spatial frequency? We use that Fourier transforms to calculate the diffraction pattern and then to calculate the image. Well, the spatial frequency is sine theta divided by the wavelength. So if I put the OPD in terms of sine theta, I can put sine theta in terms of spatial frequency. And therefore, I can see how much the optical path difference varies as a function of the spatial frequency f. And that will simplify some calculations. So this small angle approximation is often employed when it's appropriate. It's also called a paraxial approximation. Paraxial means near the axis. In this case, near the optical axis. So small angles means my rays stay near the optical axis, and this is in fact the paraxial approximation to the optical path difference. So defocus causes a phase error, and at least in the case of small angles, the phase error goes approximately as the spatial frequency squared. So small spatial frequencies don't have much phase error. The larger the spatial frequency, the larger the error caused by defocus. For a line space pattern, we know that the zero order will be right in the middle of the lens, and therefore it will see no phase error. I'm assuming we're using conventional illumination, normally incident on the mask. The first order occurs at spatial frequency of 1 over the pitch. Minus first order occurs at minus 1 over the pitch. So we'll see a phase error that's proportional to f squared, in other words, proportional to 1 over the pitch squared. A couple of things there. We see that I get the same phase error for the plus first order and the minus first order because I'm squaring the spatial frequency. The result is a phase difference between the 0 and the first orders. 0 order sees no phase error due to defocus. The first order does. Therefore, there's a phase difference between 0 and first order. The result is less interference. Remember, when the beams are in phase, I'll get complete interference between them. If the beams are out of phase, I will get no interference. I'll get less interference, and we'll find out that, in fact, if we have a certain phase difference, we can get no interference whatsoever between them. 90 degrees being that. We'll talk about that later. We also see that the amount of phase error is proportional to 1 over the pitch squared. So smaller pitches experience greater phase errors. This will be very important. Large features experience the effect of defocus much less than small features do. And finally, as I was hinting at, when the phase difference between the 0 and first orders equals 90 degrees, the 0 order and first order are at right angles to each other, from a phase perspective, they do not interfere at all. And without any interference, I don't get an image. We can go out of focus so far that our image disappears completely. Let's review that using the picture that we've seen already. The 0 order plus and minus first order combine at best focus at a plane where all the rays arrive in phase. And then if I'm out of focus, either too far away from the lens or too close to the lens, then I see a phase difference because the first orders travel a different distance than the 0 orders. This 3-beam imaging has the highest sensitivity to errors in focus. Now, let's consider 2-beam imaging. We saw that we could create 2-beam imaging using off-axis illumination. We just tilt the illumination so that the 0 order lands over here and the first order lands over here. There's another way to do it with something called phase shifting masks. We're not really going to talk about that, but that is an approach that also achieves 2-beam imaging. Now, let us further suppose that we are symmetrical in our arrangement here. That is, I tilt the illumination so that the 0 order lands on one side of the lens, and then for a particular pitch, I'll get a first order landing down here. And if I adjust the angle of illumination just right for this particular pitch, I can make the 0 order and the first order symmetrically placed about the center of the lens. What does that mean? It means when I look at these two rays arriving in focus, that is, in phase when they combine at the wafer, and now I move the wafer to be out of focus, well, look, both of these rays travel the same distance to get to the new wafer location. If they travel at the same distance, they have the same error in phase. If they have the same error in phase, there is no phase difference. Only phase differences matter. Phase is a relative thing, so only if we have a difference in phase can we even notice what the phase is. So with no phase difference, I won't see any impact due to defocus. 2-beam imaging has the lowest sensitivity to focus as long as I adjust my 2 beams to be evenly spaced about the center of the lens. And this is in fact the main reason why we use 2-beam imaging. Well, one of the 2 reasons. One is we can print smaller features with 2-beam imaging, and the other is we can get imaging that is much less sensitive to going out of focus. Both of these are very important for lithography, which is why most of the high-resolution lithography done today uses 2-beam imaging rather than 3-beam imaging. All right, Let's go back, however, to 3-beam imaging and use an example. We'll have some 2-beam imaging in the homework, but for the example we work out here in these lectures, let's look at the case of 3-beam imaging and equal lines and spaces. We'll assume that we have coherent illumination, normally incident plane wave illumination on the mask, equal lines and spaces, and a numerical aperture such that only the 0 and the plus and minus first orders go through the lens. This is the imaging example that we've worked out a couple of lectures ago. And we saw that the diffraction pattern that travels through the lens looks like this. So T sub m of f of x is the diffraction pattern. The electric field of the diffraction pattern is a function of the spatial frequency. And P as a function of f is the pupil function of the lens. The pupil function of the lens is the equation of a hole. It simply is 1 inside the lens and 0 out. So the product of these two is the portion of the diffraction pattern making it through the lens. And what do we see? Well, we've got the 0th order here, has an amplitude of 1/2, and the delta function, the point of light that represents the 0 order, occurs at the spatial frequency of 0. The plus first order has an amplitude of 1/pi. It's a delta function, a point of light, that occurs at a spatial frequency of 1 over the pitch. And the minus first order also has an amplitude of 1/pi, and it is at a spatial frequency of minus 1 over the pitch. Now, when we defocus by an amount delta, this is equivalent to adding a phase error to the orders. What is it? What kind of a phase error? Well, to the 0th order, it doesn't add any phase error. But to the plus and minus first orders, it does. The amount of phase error, this delta phi term, will be related to the optical path difference, the OPD. And as we saw, and we've discussed in the past, light is a wave, so every wavelength, it goes through 360 degrees of phase, or 2 pi in phase. So to convert the optical path difference to a phase difference, I simply need to multiply by 2 pi, 360 degrees, and divide by wavelength. That converts distance to phase. We also derive the, or I gave you, didn't quite derive it, but I gave you the equation for the optical path difference. It was the defocus distance times 1 minus cosine theta. Therefore, here is our phase difference. 2 pi defocus distance times 1 minus cosine theta divided by lambda. And cosine theta is related to sine theta, and thus the spatial frequency here. So this is the exact expression. We also mentioned a paraxial approximation to that expression as well, which is just the first term of a Taylor series expansion of the square root. Now let's apply this phase error to the plus and minus first orders. What does that mean? Well, the 0 order, nothing happens to it, no phase error. But the plus first order and the minus first order, I simply multiply by a factor e to the I delta phase. This is how we represent a phase error in terms of electric field, e to the I phase. It's a mathematical expression of a change in the phase. So I've changed the phase of the plus 1 order and the minus 1 order by the same amount, and I multiplied those two terms by e to the I delta phi. Now we can calculate the image just as we had before. We take the inverse Fourier transform of this equation, and here's the result. The resulting electric field of the image is 1/2 plus 2/pi e to the I delta phi times the cosine. Now, if you recall what our answer was before, it looked just like this, but without the e to the I delta phi term. In other words, this is the only difference when I include the impact of focus. When I'm in focus, e to the I delta phi is simply 1, because the delta phi is 0. So the in focus electric field is obtained from this same equation. Well, electric fields are fine, but it's the intensity of the light that the photoresist responds to, and we see So the intensity is going to be more important to us. I take the magnitude of this term squared, and you can work out that math fairly easily. You find the intensity of the image is given here. What do I have? Well, first I have a 1/4. All right. Well, you can imagine if I simply take this term and square it, that comes from 1/2 squared. In other words, the zero order produces this DC 1/4 term. This last term, which has a cosine of 4 pi x over the pitch, this comes from the plus and minus first orders interfering with each other. And notice that there's no phase error term there at all. The plus and minus first orders have the same phase. So adding some phase to the plus and minus first order doesn't affect how those two orders interfere with each other. And that term disappears. The phase part of that term disappears. On the other hand, the plus and minus first orders interfering with the 0th order produce the middle term. This is the main sinusoidal variation that we see in our image. It's the sinusoidal variation we're trying to achieve, and you see that it has a pitch of p, cosine of 2 pi x over p. The period is the pitch. This is the period we're trying to achieve, and therefore this is the modulation, the up and down of the image that we're hoping to get. And the amplitude of that variation now has a new piece, cosine of delta phi. So, if delta phi is 0, this cosine is 1. I've got the maximum amplitude of my variation in the image. As delta phi grows, this variation gets smaller and smaller. And if delta phi turns into 90 degrees, cosine of 90 degrees is 0. And the up and down at the period of my mass pattern, that variation disappears completely. I no longer have an image that resembles my mask. So 90 degrees, pi over 2 phase error applied to the first orders is enough to completely wipe out our image. Here's a graph of what those images look like. When I'm in focus, I have the highest intensity in the regions of the space. I have the lowest intensity in the regions of the line, and the steepest slope near the edge. So line, space, repeating and repeating. Now, as I go out of focus, this modulation, this variation from bright to dark gets less and less. The intensity of the light in the bright regions gets dimmer. The intensity of the light in the dark regions gets brighter. And the slope, the variation near the edge of the mask feature, gets less and less. In other words, the image gets blurry. All right? I can't recognize the difference between the bright areas and the dark areas nearly as well when I'm out of focus compared to when I'm in focus. So this gives rise to an interesting question. What is the maximum range of focus that we can tolerate? Well, when we're out of focus, the image gets blurry. As I just mentioned, the intensity in the space region goes down, the intensity in the line region, which we want to be low, goes up, and the slope of the image at the line edge decreases. This is what we mean by blurry. When we say the image is blurry, it's harder to see where the edges are. We define the depth of focus as the amount of defocus we can tolerate before these problems become unacceptable. There's enough blurriness, enough loss of slope at the line edge that we can no longer adequately differentiate between what is a line and what is a space. The range of focus we can tolerate is called the depth of focus, and it's the full range from both plus to minus, because the middle of that range is where I'm at best focus. Lord Rayleigh, that was his official title, John William Strutt was his name, defined depth of focus using a maximum phase error of 90 degrees. As we saw, when the phase error reached 90 degrees, or a quarter of one wavelength in terms of optical path difference, then the first order would not interfere with the 0 order, and we'd get no modulation, and the image would disappear. So this is the maximum you could possibly tolerate and still even notice that there's an image there. Lord Rayleigh, by the way, also invented the resolution criteria that we saw a few lectures ago. He was a famous gentleman scientist, a little more famous than me. He won the Nobel Prize for his discovery of argon, did a lot of work on the theory of sound, and a lot of work on optics. He was studying the optics of telescope imaging, but the principles are the same. So, if the OPD is delta, the defocus distance, times 1 minus cosine theta, and as Lord Rayleigh said, the maximum OPD we could tolerate has to be less than 1/4 of a wave, I can simply take this maximum 1/4 of a wave and plug it in here and use that to calculate the maximum defocus I can tolerate. The depth of focus is simply 2 times the maximum defocus I can tolerate, because there's a plus side and a minus side. The errors are symmetric. So the depth of focus then is something less than 1/2 lambda over 1 minus cosine theta. What Lord Rayleigh did, though, is approximate 1 minus cosine theta with its paraxial approximation. The reason was, in the days of Lord Rayleigh, all of the angles were small. We didn't have any large numerical aperture lenses, so all the angles at work were quite small. And if we use the small angle approximation, 1 minus cosine theta is about equal to 1/2 sine squared theta. And therefore, our depth of focus has to be less than lambda over sine squared theta. Well, what is sine squared theta? It's the angle of the light coming out of the lens, and if we have a periodic line space pattern, then that's the angle of the first order. Well, sine of theta divided by lambda is simply 1 over the pitch for the first order, so I can plug that in. So for the first order case, a case where I'm only getting the 0 and plus and minus first orders, we find that the depth of focus is proportional to the pitch squared and inversely proportional to the wavelength. What does this tell us? Something very important and very fundamental. Small features have less depth of focus. This is one of the reasons that lithography is so interesting. I'll use that word. Challenging. We try to print smaller and smaller features, and as we do, we get less and less depth of focus. That is, we can tolerate less and less amounts of focus error before our image becomes unacceptably blurry. For the case of imaging at the resolution limit, which is, of course, something we try to do a lot, we push that diffracted order right to the very edge of the lens, and sine of theta is going to be equal to the numerical aperture. So if I use the numerical aperture in place of sine theta in this equation, I find that the depth of focus has to be less than lambda over NA squared, or what we commonly do is throw a proportionality constant K2 to make it an equal sign, and we see that the depth of focus is some constant K2 times lambda over NA squared, where we know that K2 has to be less than 1. Maybe it's 0.8, 0.7, something, but we know it has to be less than 1. This equation is generally called the Rayleigh depth of focus equation, or the Rayleigh depth of focus criterion. And we have a Rayleigh resolution equation and the Rayleigh depth of focus equation. And these are commonly referred to in the industry. It's very, very important that we understand all the assumptions that went into the Rayleigh depth of focus equation, because we use this equation or refer to it quite a bit in our industry, and it's often misused because people don't remember all the approximations and assumptions that go into the Rayleigh depth of focus equation. So what are they? First of all, I'm assuming 3-beam imaging. This equation doesn't mean anything if I have 2-beam imaging. Right? Lines and spaces where only the 0 and plus and minus first orders are being used. It assumes low numerical apertures, less than about 0.5, because we're using the paraxial approximation. We're assuming all of our light is coming in at small angles. We're also assuming, and here's a big one, we're also assuming that the feature we're trying to image is at the resolution limit, because we're assuming the first order is right at the very edge of the lens, so that we could replace the sign of the angle with the NA, the numerical aperture. Further, to use this equation, we have to know K2, and K2 is unknown until we actually go make some measurements of what the depth of focus really is. All that we know is that K2 must be less than 1. And from experience, it's often in the range of about 0.8. So, that's a lot of assumptions, a lot of restrictions. If we're trying to use the Rayleigh depth of focus equation when these restrictions don't apply, we're making a mistake. And in fact, this really doesn't work for the lithography we do today. We're always at larger numerical apertures. We're often looking at features that aren't exactly at the resolution limit. Often we're using 2-beam imaging rather than 3-beam imaging. So the Rayleigh equation, as it's usually quoted, is not that useful, but it's useful for you to understand it because people still use it even if they're making a mistake. So, what have we learned in Lecture 46? As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material. How does defocus affect the optical path difference of light exiting an imaging lens? What is the paraxial approximation? And how do we apply that to our understanding of defocus? Name 3 things that happen to an image as it goes out of focus. What is the Rayleigh depth of focus equation? This is a common enough equation that you should commit it to memory. And finally, and maybe even most importantly, especially if you memorize the Rayleigh depth of focus equation, what assumptions were used in the Rayleigh depth of focus equation that don't often apply to lithography today? Well, that's Lecture 46. In fact, it's our last lecture on forming an image. We've learned about how to form an image, how to calculate what that image is, and what the effects of defocus on that image are. We have a little bit more to do with optics, and then we're about to start in photoresist.